Hi, in this video we are continuing from the previous one where we established the baseline multitask estimator, and then we saw how top item selector would be calling the estimator for all the items that are retrieved, and so the estimates would be like one for each task, and then this top item selector would do a weighted sum of these estimates into a single score, and then sort based on that. And in our simple example, the top item selector was choosing a single item. It was top item is torch.argmax, but in more generally you can select more than one item. Okay. So today we are continuing from there, and we'll look at the implementations of causal debiased ranking. So multitask estimator we covered, and let's look at position debiased estimator, which is a small extension on top of the multitask estimator. So in addition to the multitask estimator, it also looks at it uses the position feature. So actually, if you go back to our diagram, then it uses the position feature, and using an sort of a neural network model, module arc, it computes estimates for all the tasks. So here you're trying to learn what is the probability of all of these tasks purely based on the position. And the idea is that some amount of the observed um, label is because of the position, and the rest is explained by other features. Now, this is an opinionated factorization. There are papers that say that this is too simple a formulation. And this is a fair point. We are just starting here, and you can do a lot more than this. I recommend looking at the entire literature of position debiasing in this context, selection debiasing, position debiasing in this context. But here we are starting this implementation because it naturally lends to other forms of debiasing. And while it can be improved, this is not a and it's not a bad start. You will see it has been implemented, and it has been successful in some publicly talked about recommender systems implementations like YouTube Watch Next. If you look at this paper that's referenced in the Substack post, you'll see an implementation of this shallow tower approach. This is called the shallow tower approach primarily because this neural network processing the position is very light. Just with one feature of the position, it doesn't need to be very complex. Okay, so coming back, we this is a position embedding arc, which takes the position feature and sort of hashes it into a small zone. Here I've assumed that probably you don't have more than 100 positions, so this should be fine. And then you have a shallow tower, which takes this embedded position feature and outputs a logit for each of the tasks. So as before, we process our features. We also process the position feature, and in the forward function, we process the features, so both the original user item features and the position feature. The original user item features are fed into the user item arc. So if you go back, this part is what I'm talking about. The input to this NN is this combined features here, and then the position feature is used by the position-based estimator. And finally, we just sum these two logits. As described, we sum these two logits. Now we'll look at the causal debiased ranking. Let's see, factorize estimator, right? So here, this extends the position debiased estimator. So in addition to whatever the position debiased estimator does, we also have a user-only arc and an item-only arc. So later on, you'll see that this module is only processes user features, and this only processes item features. And then there is a gating arc, which the output dimension is 4. Its job is to come up with the weights, the importance weights for the four arcs. So now let's look at the diagram. As I mentioned, we have user only arc, which only looks at the user features and comes up with user only estimates. You have an item only arc, which only looks at the item features and comes up with item only estimates. You have a gating arc, which looks at all these features, and potentially it can look at the position feature also. I just haven't implemented it that way. And it needs to output weights. Probably here the weights sum up to 1 is a good assumption to make, but it needs to output weights by which the output logits are multiplied. So item only logits into W3 is this iLogits thing. Similarly here. And then it's summed up. So here we are adding two affordances. One is we are adding logits, but that are purely computed based on user features, and similarly on item features. The sort of thing you expect to learn is, maybe there are cohorts of users or explainable cohorts of features cohorts of users who have a high probability of taking one of the observed actions. Let's say in a podcast recommendation system, you have power users who, sort of maybe definitely use your application every day driving to work or something. So if you are able to see that based on the illness of the user, the how many times they have come in the last 28 days, it allows you to predict with a reasonably high confidence that, hey, power users are going to listen to the recommendations. I don't know, maybe the probability of listening is zero point 0.3, and non-power users or cold start users, maybe the general intrinsic probability of listening is like 0.05. So that sort of large bias you can capture. Let's say the mental model, you can try to capture the user mental model coming in through this arc. And similarly on the item side, maybe your recommender system has a popularity bias. Back in the day, I think, YouTube, etc., there was a lot of popularity bias, and it's a fair claim to make that videos that are trending will be viewed at a higher rate if they are recommended than videos that are not. So those sort of features you can input as item only features, and you can observe those tendencies of viewers in general through this arc. So let's look at the code again, and we'll try to map it to the diagram. So you have in the process features, you take the IDs, the user and item IDs, you pass it through your embedding arc. This is similar to the multitask estimator. I just have had to write this again because we are making quite a bit of changes, and the output of this function is different than the multitask estimator. But yeah, you're processing the same things at the estimator, and transforming these user item features, cross features, the position feature again through an embedding arc. Now, instead of just one output, which we call combined features, now we have three: user only, item only, and user item. And you have the position arc input, which is nothing but the embedding arc. So now there are four things that this process feature sends, and after it sends them, each of those are sent to their corresponding arcs. The user item logits takes the combined, and the position arc, user logits, and item logits. So till this point, what we have done is computed the output of these arcs of this layer. So position logits, user only, user item, and item only. After that, we are computing the gating weights, running a softmax on them. This is to make sure that they sum up to 1 and they're all positive. And then we are computing, like, this is essentially computing a weighted sum. to get the final logits. So this is computing a weighted sum to get the final logits. And that's what we are returning. The forward function is just the final logits. Thanks.